In the Beginning by Dr. Walt Brown. We'll take a look at supercritical water here on page 136 of In the Beginning. Okay. 3 common questions. Those not familiar with the behavior of high-pressure fluids sometimes raise 3 questions. 1. How could rock float on water? The crust did not float on water. Water was trapped and sealed under the crust. Water pressure and contact points, called pillars, between the chamber's sagging ceiling and the chamber floor supported the crust. The crust was like a thin, dense slab of rock resting on and covering an entire waterbed. As long as the waterbed mattress does not rupture, the dense slab will rest on top of less dense water. Unlike a waterbed seal, which is only a thin sheet of rubber, the chamber's seal was compressed rock 30 to 60 miles thick. Pressures 5 miles or more below the Earth's surface are so great that rock deforms like highly compressed, extremely stiff putty. Therefore, the slightest tension crack could not open from below. 2. The temperature increases with depth inside the Earth. 2. Temperatures increase with depth inside the Earth. Subterranean water about 60 miles below the Earth's surface would have been extremely hot. Wouldn't all life on Earth have been scalded if that water flooded the Earth? No. Today's geothermal heat is a result of the flood. Let's first understand tidal pumping. That continually heated the supercritical subterranean water, a very high energy, explosive form of water discovered in 1822. Besides, the expanding fountains of the Great Deep became very cold. Besides, the expanding fountains of the Great Deep became very cold. See Rocket Science on page 589. Tidal pumping. Tides in the subterranean water lifted and lowered the massive crust twice daily, stretching and compressing the pillars, thereby generating heat and raising the temperature of the subterranean water. As quartz and certain other minerals dissolved, this hot, high-pressure water increasingly contained the ingredients that would later produce limestone, salt, and other forms of quartz. In a few chapters, you will see why, after the flood, this dissolved quartz petrified some wood and cemented loose flood sediment into sedimentary rocks. Supercritical water. At a pressure of 1 atmosphere, about 1.01 bar, or 14.7 pounds per square inch, water boils at temperatures slightly above 212 degrees Fahrenheit. As pressure increases, the boiling point rises. At a pressure of 3,200 psi, the boiling temperature is 705 degrees Fahrenheit. Above this pressure temperature combination, called the critical point, water is supercritical and cannot boil, nor will any amount of pressure liquefy the water vapor. The pressure in the 60-mile deep subterranean chamber, simply due to the weight of the crust, was about 372,000 psi, or 25,650 bars, far above the critical pressure. As the denser and thicker portions of the crust sagged in places and settled to the chamber floor, it lost potential energy, which was gained as heat by the subterranean water. That water then became supercritical, exceeding 705 degrees Fahrenheit, and to a degree ionized. Supercritical water can dissolve much more salt per unit volume than normal water, up to 840 degrees Fahrenheit. At higher temperatures, salt precipitates, outsalts. In a few pages, this fact will show why our oceans have so much salt and how salt domes formed. Supercritical water consists of microscopic liquid droplets dispersed within every... Supercritical water consists of microscopic liquid droplets dispersed within very dense water vapor. Hot droplets cool primarily by evaporation from their surfaces. The cooling rate is proportional to the total surface area. The smaller a droplet, the larger its surface area is relative to its volume. So more of this heat is quickly transferred to its surroundings. Liquid droplets in supercritical water have an area to volume ratio that is a trillion times greater than that of the floodwater that covered the Earth's surface. Consequently, the liquid in supercritical water cools almost instantly if its pressure drops, because the myriad of shimmering liquid droplets, each surrounded by vapor, can simultaneously evaporate. A typical supercritical water droplet at 300 bars and 716 degrees Fahrenheit consists of 5 to 10 molecules. These droplets evaporate, break up, and reform rapidly and continually. This explains how the escaping supercritical liquid transferred its energy into supercritical vapor. How did the vapor lose its energy and cool? Rapid expansion. A remarkable characteristic of supercritical fluids is that a small decrease in pressure produces a gigantic increase in volume and cooling. So as the supercritical water flowed toward the base of the rupture, its pressure dropped, and the vapor portion expanded and cooled to an extreme extent. See Rocket Science on page 589. As it expanded, it pushed on the surrounding fluid, liquid and gas, giving all fluid downstream ever-increasing kinetic energy. As the horizontally flowing liquid-gas mixture began to flow upward through the rupture, the pressure steadily dropped in each bundle of supercritical fluid. This released its electrical ionization energy, and some of each liquid droplet evaporated to become vapor. Within seconds, portions of the flow rose above the atmosphere, where the pressure was almost zero. This 10,000-fold expansion was a weeks-long focused explosion of indescribable magnitude, splitting the atmosphere and accelerating much of the water, along with rock and dirt, into the vacuum of space. In summary, as the flood began, supercritical water jetted up through a globe-encircling rupture in the crust, as from a ruptured pressure cooker. This huge acceleration expanded the spacing between water molecules, allowing flash evaporation, sudden extreme cooling, followed by even greater expansion and acceleration and cooling. Therefore, most of the vast thermal, electrical, chemical, and surface energy in the subterranean water ended up not as heat at the Earth's surface, but as extreme kinetic energy in all the fountains of the great deep. As you will see, these velocities were high enough to launch rocks. As you will see, these velocities were high enough to launch rocks into outer space, the final dumping ground for most of the energy in the supercritical water. Three, what happens as a fluid becomes supercritical? Key experiments in 1822, French Baron Carguenard de la Tour performed a famous experiment. He sealed a specific amount of liquid inside a strong glass tube. The meniscus, the boundary between the liquid below and the vapor above, was visible. As he heated the tube, some liquid evaporated. Therefore, the pressure inside the tube and the vapor's lower density steadily increased, but as temperatures rose, the liquid's higher density slowly decreased. When the two densities became equal, as a specific temperature and pressure, now called the critical point, the meniscus disappears. Was the substance a liquid, a vapor, or something else? For almost 2 centuries, no one knew. In 2005, scientists in Germany, France, Sweden, and the Netherlands, and the United States published experiments on supercritical water showing that both liquid and vapor were present. The liquid consisted of microscopic droplets floating throughout the dense vapor. A thought experiment. What follows is conjecture. To my knowledge, no one has described the microscopic behavior of supercritical fluids as I will below. But based on the 2005 experiments, the physics now seems clear. If we would view the meniscus in microscopic detail as the temperature approached the critical point, I believe we would see the following. The liquid below the meniscus becomes increasingly agitated and resembles a choppy lake on a windy day. The liquid and vapor are nearly in equilibrium, so about as many molecules evaporate from the liquid as enter the liquid from the vapor. At these very high temperatures, vapor molecules strike the liquid surface at a furious rate and splash droplets of liquid up into the denser vapor. As the vapor's density approaches the liquid's density, the droplets float in the vapor. This process continues until all liquid below the meniscus is dispersed as microscopic droplets in the vapor, so the meniscus suddenly disappears. The shimmering droplets suspended in the vapor are then bombarded from all directions by vapor molecules acting as bullets. When these bullets strike a droplet, they either fragment the droplet, stick to it, or bounce off the droplet. Droplets quickly fragment, merge, or evaporate. Would these microscopic droplets float on the top of the vapor? No, but let's assume they did. It would mean that the vapor was denser than the liquid droplets. Vapor molecules would be closer to each other on average than liquid molecules. Therefore, vapor molecules would frequently bond with each other and become liquid droplets. The presence of liquid droplets throughout the supercritical vapor contradicts our assumption that all the liquid had floated to the top of the vapor. With a little thought, it should become clear that liquid droplets almost instantly form and disappear within the dense vapor. With water, H2O, the molecules, when fragmented, ionized, become electrically charged particles, H plus and OH. As temperatures rise, the vapor molecules travel faster and fragment more droplets. The droplets become, on average, even smaller. They also collide and merge more frequently, so equilibrium is quickly reached at each new temperature with an equal number of droplets forming as disappearing each second. Energy is expended in fragmenting droplets because work must be done in stretching and breaking molecular bonds in the liquid phase. Most of the energy expended in fragmenting molecules become ionized, electrical energy. If the pressure drops, electrical energy is recovered and surface energy is given up, so the volume expands explosively. The faster the pressure drops, the more explosive and cooler the expansion. Thermal energy becomes kinetic energy. When the flood began, the pressure in the jetting supercritical water dropped in seconds. Okay, when the flood began, pressure in the jetting supercritical water dropped in seconds from at least 372,000 psi to almost zero above the atmosphere. In later chapter, you will see how nuclear reactions significantly increased this pressure during the early days of the flood. The energy released was huge because the 46,000-mile-long fountains continued this release for several weeks. One should not think of it as a single explosion. Instead, the jetting water was a powerful, Earth-size nuclear engine that launched considerable mass from Earth. Great solubility. Today, supercritical fluids, usually water or carbon dioxide, are studied primarily because of their great dissolving power. In 1879, J.B. Hannay and J. Hogarth first demonstrated this. When they rapidly dropped the pressure in a supercritical fluid, the dissolved material precipitated as falling snow. Why is the solubility of supercritical fluids so great, and why did the solute precipitate so rapidly? Supercritical liquid droplets impacting solids, like a dense spray of bullets, each slightly larger than a gas molecule, will penetrate, break up, and dissolve more of the solids than will pure liquids. Also, as described above, the liquid droplets almost instantaneously form and evaporate. When they evaporate, the dissolved solids precipitate outsalt as sediment onto the floor. When new droplets form from merging vapor molecules, they contain no solute. and can then dissolve more of the solid they encounter. During the flood, the escaping subterranean waters swept most of those loose precipitated sediments on the chamber floor up to the Earth's surface. Therefore, supercritical fluids can dissolve large quantities of organic material and certain minerals. If the pressure in the supercritical fluid suddenly drops, the liquid evaporates explosively and the solids precipitate as snow. Common precipitates from the subterranean water were limestone, salt, quartz, and various ores. Supercritical water. This was page 136 and 137 in Dr. Walt Brown's book, In the Beginning, Compelling Evidence for a Creation and a Flood. Available at hpt.rsr.org.